Okay, so let's take another question. In this question, we are given two circles which touch each other at a point C. Okay, let's draw a circle which touch each other. So this is the one circle, circle A, and this is the another circle, circle B. And these two circles touch each other. They just touch. They don't intersect, okay? So we can draw like this also. But in this case, they intersect. Okay, they don't touch. In this case, these circles touch each other. Okay, so what the question says that the two circle touch each other at point C. And what we have to prove that the common tangent at C, this is the point C, where they touch each other. This is point C, this point. Okay, then we have to prove that the common tangent. Okay, let's see common tangent first. What is common tangent? Suppose if you have two circles, two any circles, they don't touch each other, two arbitrary circles. So let's this be a circle, circle A and circle B. So how many common tangents we can draw? Do you have any idea how many common tangents we can draw? Common tangents means if uh, let us suppose draw a tangent here. So no matter how much we extend this line, it's this line is never going to touch this circle, though it's a tangent for this circle, but it's not for this circle. Okay, so how how many common tangents we can draw? So this line will never intersect the other circle. So let's again look. Suppose we have a point here and we have a point here, and we can, as you know, we can always connect 2 points. Okay, so let's try to connect these 2 points. Okay, this line touches this circle at this point. Let this point be O and this point be P. Okay, and this. So this is the common tangent. We can also take point somewhere here and then somewhere here, but again this won't be a common tangent. It's neither a tangent for this nor for this, because it passes through the circle. And the condition for tangent is it should always touch the circle at one point only, one and only one point. Okay, so this is not the tangent. And we can draw one more tangent. Let us take this point and this point. So we can always draw a line like this. So what is an important observation here? The first important observation is we can draw two common tangents tangents for two given circles, two given circles. Okay, and no matter how much hard you try, you can never find a line which is tangent to both the circle, more than two. These two lines we know, but okay, let's try here. Okay, this is a tangent to this circle, but this line is never going to intersect or touch. It's not even going to intersect this circle. Forget about touching. Then if we take another like line, this, so it's tangent to this circle, but this is never going to touch this circle. So one important observation is we can always draw two common tangents for two given circles. Okay, this is the first important observation. Now, special case of this. What happens when the circle touch each other? When the circle itself touch each other. Okay, let us suppose again these are two circles which touch each other at some point C. So how many common tangents we can draw? Obviously, two we can draw for sure, as we have seen in the previous case. And we can draw one more common tangent from here. Okay, so what is an important observation here? That we can draw three common tangents. Okay, so this is the special case of this first case, and this is a special case. In this case, we can draw three common tangent for two given circles. Okay, so with these things in mind, let's try to solve this question. So the question says that the common tangent to the circle at point C, this is a common tangent to the circle at point C, bisects the common tangent. Now this is the another common tangent. This is the common tangent. Bisects the common tangent. This is the PQ, common tangent PQ. So we have to prove that this common tangent, let this be line L. So, and this intersects at R. So we have to prove that this line bisects the line PQ, which means, mathematically it means we have to prove PR is equal to PQ. Common tangent bisects the common tangent at PQ. That means we have to prove PR is equal to PQ. So again, how to do this? So let's look at it from a different point. So this is a point R, and we have two tangents from this point, PR and RC. Okay, and these two tangents are going to be equal. This is equal to this. Okay, and again, so let's write this. We have PR is equal to RC. Why PR is equal to RC? Very easy. If we draw like this, we draw the perpendiculars from here, and as this is tangent, PR is tangent and RC is also tangent, so this angle is 90 degree. Mark this angle as 90 degree. Okay, and join this line. So we have this radius, and this is also radius, which is equal, and we have this common side, and this angle is 90 degree. So these two triangles are congruent. How they are congruent? By RHS criteria. Okay, RHS criteria, these two triangles are congruent. This triangle and this triangle are congruent. Similarly, for this case also, if we'll draw the radius here, okay, and then we'll join this. So again, what we have, radius equal to radius. Let's take some different color. This is radius, and again this is 90 degree. This is a tangent, this is also tangent, 90 degree, 90 degree, and again this side is common. So by RHS criteria, again these two triangles are congruent, and if they are congruent, the corresponding sides are equal. That means, what are the corresponding sides? That means this side RC is equal to RQ. Yeah, so let's write it. RC is equal to RQ. And also, as these two triangles are congruent here, this triangle and this triangle are congruent, so which two sides are equal? PR is equal to again RC. So let's write this. PR is equal to RC. So from these two, what we can conclude is all the three sides are equal. PR is equal to RC, and again RC is equal to RQ. So obviously this PR is equal to RQ, hence proved.